So we're going to put determinants to use here. So you can see particularly the singular property is going to be of great use along with this one term expansion here. That's how we're going to relate eigenvalues and determinants. Okay, so we need to find lambda such that A minus lambda I is singular, right? This is our eigenvalue problem, isn't it? We need to find lambda such that A minus lambda I is singular. Now we have a condition for singularity, right? It's the same as determinant A minus lambda I being equal to 0. So we get one very nice condition relating, in terms of lambda, which gives you all the eigenvalues. Anytime lambda is an eigenvalue, determinant A minus lambda I has to be 0 because A minus lambda I has to be singular. Okay, that's the nicest thing. So now how do we think of this A minus lambda I? A is this matrix, let's say. What is A minus lambda I? You simply subtract lambda from the diagonal elements, A11 minus lambda, so until ANN minus lambda. All the upper triangular part remain the same, lower triangular part remain the same as A, right? Only the diagonal you subtract lambda. And determinant A minus lambda I. Now what do we know about determinant? It has one term which is the product of all the diagonal elements, right? That will have a lambda power n term. It could be either minus lambda power n or plus lambda power n, right? But it will have a lambda power n term. That lambda per n term will not be cancelled by any other term. The reason is every other term has at least one element here or one element here, which means it can have degree at most lambda power n minus 1, right? So the lambda power n can never be cancelled. So determinant A minus lambda I is a polynomial in lambda with degree n, okay? An n degree polynomial has at least n complex roots, and those roots are the eigenvalues of a matrix A, or if it represents an operator T, it's for that operator T. Okay, so it's a very nice way to compute eigenvalues using the matrix representation, using the determinant in this way. Okay, so it's just, at least theoretically, is easy to see. Okay, let's look at n equal to 2. A is A, B, C, D. Determinant A minus lambda I is a quadratic equation. It's just A minus lambda times D minus lambda minus BC equal to, if it's a quadratic polynomial, you equate it to 0 and solve it, you get the 2 eigenvalues. For n equal to 3, likewise, it will be a slightly more complicated expression, but you can write it out. You see that this term has a lambda per 3 term. It's a cubic polynomial, equate to 0. You can find all the eigenvalues. Okay, so determinants give you a very, very easy way to do it. Here are 3 problems. You can try each of these problems. Let's at least try one of them and see what happens. So let me try the first one, 1, 2, 3, 2, 3, 5. Okay, so it's actually very easy. Let's try this one. A equals 1, 2, 3, 0, 2, 3, 0, 0, 5. So A minus lambda I is 1 minus lambda, 2, 3, 0, 2 minus lambda, 3, 0, 0, 5 minus lambda. Or determinant A minus lambda I. What do I know about determinant? Determinant of an upper triangular matrix, right? This is upper triangular. If you have an upper triangular matrix, determinant is just the product of the diagonal terms, because all the other terms will involve some term from the lower triangular part, and that will go off to 0. So it's just 1 minus lambda times 2 minus lambda times 5 minus lambda. So it's a degree 3 polynomial, but it's already factored, right? So if you say 0, then lambda is going to be 1, 2, 5. So the eigenvalues, are 1, 2, 5. Great, isn't it? Quite easy. Let's try one more problem. 1, 0, 1, 0, 2, 0, 1, 0, 5. Okay, so A equals 1, 0, 1, 0, 2, 0, 1, 0, 5. So what is A minus lambda I? 1 minus lambda, 0, 1, 0, 2 minus lambda, 0, 1, 0, 5 minus lambda. Let's see what happens to this guy. So I have to do determinant A minus lambda I is 1 minus lambda. See, notice how I do it. I start with this value 1 minus lambda, and then I do determinant here, right? What is determinant of this? It's 2 minus lambda into 5 minus lambda. I know it's minus 0 times something, I don't have to bother, right? Minus 0 times something will go away, and then I have plus 1 times determinant of this guy. Determinant of this is 0 minus 2 minus lambda, so you get minus 2 minus lambda. Okay, So, this is what it is, and this 2 minus lambda comes out as minus. I can take it as common. So, I get 2 minus lambda times 1 minus lambda times 5 minus lambda minus 1, isn't it? So, this will give you 2 minus lambda times, if you multiply it out, lambda squared, right, minus 6 lambda plus 5 minus 1, so it is 4. Okay. So, what are the eigenvalues? Lambda equals 2 is one solution. Here you are going to do 6 plus or minus square root of 36 minus 16 by 2, which will work out as 3 plus or minus 20, right, root 5. So, that is those are the eigenvalues that you get. Okay. So, there is one more example here. So, let me do that also, just for completeness. It was, I think it is the same sort of example, 1 0 1 0 2 0 minus 1 0. Okay. So, let us do a minus lambda I. I'm going to get 1 0 1 0 2. Just doing it laboriously. Determinant a minus lambda I is 1 minus lambda, 2 minus lambda, 5 minus lambda. So, it is minus, so plus 1 into 2 minus lambda. Okay. So, you get 2 minus lambda times lambda squared minus 6 lambda plus 6. Is that correct? I hope I did not make a mistake. So, you can solve this, you will get answers. Okay. So far we got all real eigenvalues. So, maybe let me just think this through 1 minute. Okay. Yeah, real eigenvalues so far we have got. Maybe they are not so interesting. Maybe you can try some simple cases where you get complex eigenvalues. So, here is a case where you will get okay. So, here is a simple 2 by 2 case. So, if you do a minus lambda I think maybe I have shown this example before, minus 1 minus lambda, determinant a minus lambda I will end up being lambda squared plus 1 equals 0. So, lambda is plus I minus I. So, you can think of more complicated examples. Even in 3 by 3 you can get complex eigenvalues. So, here is a simple example I will cook up, okay, just to give you a sense of how these may happen. Okay. So, here is a very simple example, and maybe this is too boring an example, I do not know. Yeah, I think you'll end up getting, oh, it's okay. So, a minus lambda I is minus lambda 0 1 0 minus lambda 0 minus 1 0 minus lambda. We'll end up getting determinant a minus lambda I will be minus lambda times lambda squared plus 1 into minus lambda. So, you will end up getting minus lambda cube minus lambda equals 0. So, that is lambda times lambda squared plus 1 is 0. So, lambda is 0 I minus I. So, you can get a whole bunch of possibilities, all sorts of possibilities exist, and you can find eigenvalues very easily using determinants, at least in hand for small examples. Okay. For larger examples, it turns out using this determinant type idea is not a great method. The earlier proof that we did, which looked more abstract, actually ends up being more interesting. The powers of t end up being more interesting, and people can look at approximate eigenvalue computation from that. Okay. Thank you very much.